stand-up physicist, here to introduce a new principle. Don't point like a drunk. Point with precision for Quaternion series quantum mechanics. So that's going to take a little explaining. So when you say to somebody on a street, hey, I work with Quaternions, I'm a Quaternions.com owner, and the first thing they say usually is, well, you know, Quaternions don't commute. Turns out that statement is not valid. And I'm using valid in a technical sense. And that is that it is true in all situations. Okay, so what does commute mean? It means A times B does not equal B times A. Well, if either A or B is a real number, then actually AB equals B times A. Okay. And if two quaternions point in the same direction, or actually if one of these guys points in exactly opposite direction, then they commute again. And B times A will equal A times B. And most people would say, yeah, but, you know, that probably never happens when you choose quaternions completely at random. And I say, yeah, you're right about that. But, you know, I think physicists don't behave like completely at random. I think they're kind of specific in how they work. So let's just imagine I'm doing experiments, okay? And I'm going to pretend I'm a sailor. And I'm further going to pretend that I've been drinking all morning, okay? And to show method acting at its finest. That's kind of strong stuff. I'm clearly a heavy drinker. Not. Okay, so I'm doing an experiment over here. You know, physicists, they're not in a wobbling like at all. As a matter of fact, I would argue that physicists are like the extreme opposite. This will require a new hat. There he is. Very, very formal. And very particular about exactly where they point. In this case, I'm pointing in the viewer's at the viewer. But that's not specific enough. I'm pointing at your left eye. Not specific enough. Your left pupil. Not specific enough. I'm pointing at the blind spot in the back of your eye on the retina, where all the nerves go into your head, so you can see this. And because I'm doing this, I can gather statistics about how often you blink. And I'm going to make a neural network model on your blinking behavior. And you say, well, that's... that guy's kind of wacko, right? Except physicists are like that, right? They collect such an enormous mountain of data. They're the ones who came up with all those neural networks in the first place that deal with the vast quantity of data that they get. And they get it from machines that are ridiculously precise in locating exactly where they are, and those machines keep on looking in exactly the same place. I mean, people keep on talking, oh, that LHC thing, you know, quite the device. Well, it actually only cares about a little volume in that 20 some odd mile radius kind of place where the two beams actually bump into each other. Of course, they bump into each other on purpose. You know, they design things like that. Or take people who study super cold atoms. Now, super cold atoms aren't all over the place. They're in a couple thousand cubic nanometer volume. it's really hard to focus on something that small in terms of area, volume, sorry. And yet physicists know how to do that. And they have to do that to collect their data. So I think if experimentalists are that precise in exactly where they're pointing, then our math tools should reflect that. Point with precision means using quaternions that all point in the same way and that all commute. You might say, yeah, but you can show, like, probably no examples of where physicists have ever done that. Not really. I actually have a rather large data set. All right, so take every quantum mechanical math expression that has been confirmed by experiments since the 20s. That's a lot of things, okay? And now write them all using quaternions of the form A, BI, 0J, 0K. It's like, cool, I suppose you could do that. Yeah, I can do that, and I'm going to do that. Because that shows that that huge volume of equations are all the type that I'm talking about. They're all pointing in the direction I times 1, 0 times j, 0 times k. So that's a large set of data that says we know how to work with quaternions that all point in exactly the same direction. So then what we can do is we can generalize this just a touch and go to quaternions of the form A, 0I, 1J, 0K. And then we can do the same for K. And then we don't have to really modify the questions, other expressions other than, swapping I for J for K. The next little baby step, and I recommend taking baby steps before running, is to go for I is 1 times 1, 1 times j, 1 times k. Does anything have to change like at all? Well, actually a little bit does. That the normalization that one uses is different. The normalization for the I 0, 0 is 1. And whereas you got to use like a 3 or something. Square root of 3, I forget. And you can further generalize this set of equations from 1925 to today and go with I times 1, j times 2, k times 3. Again, it changes the normalization factor, but every single result will be exactly the same. And then you reach the common critique, yeah, but that's boring. It's like, oh no, the dancing doesn't make it interesting either, okay? So what I say to that is, well, the great reason to do this is you understand why quantum mechanics is the way it is in terms of causality. Remember, that was really Einstein's biggest objection to quantum mechanics. Not its success. He didn't argue with that like at all. He was super impressed with Planck's work, with his own work on the photoelectric effect, with the Bohr atom, with de Broglie, or de Broglie if I pronounce it right. Schrodinger is like, but when he got to Schrodinger, it's like, hello people, come on, what's going on with causality? That you got to explain, and it hasn't. How many people talk about causality when they're talking about why quantum mechanics is? Well, you better. That's the number one issue. Okay, so let's say I've got a wave function and I've written it in terms of a 1i, 1j, 1k. What can I tell you about that wave function? And we all know nothing. What you need to pair up with that block of information, whether it's finite or infinite, is its conjugate. And I'm going to get this wrong because it's got to be minus I, minus j, and minus k. Let's see. I don't know that... I might have to break some fingers to make this work. All right, so in a hand-wavy way, these are all minus of this. All right. So what do we know about the causal relationship between all the information here and its reflection, 3D reflection here? What we know about the causal relation is that these events, or energies, whatever they are space-like separated from these. Because the time is the same. We didn't flip the sign of the time. But all the spatial things, they all got flipped. And so if they're at the same time, and they're at different locations, then it's necessarily the case that these are space-like separated. And so it's it's this bizarre situation. Well, they're space-like separated, but every bit of information is exactly replicated over here. It's like, well, that's weird. Yeah, that's quantum mechanics. Okay? But we have explained non-locality, why non-locality has got to be there. And we've done it in the most boring possible way, saying, hey, just write I as IJK. But we had to combine it with this new principle about being not pointing like a drunk, but pointing with precision, always in exactly the same way, because that's the way experimentalists do their work. In other words, we're using math tools, Quaternions, that can work in space-time because they got 4 slots, and they're precise, therefore they're all pointing in exactly the same direction, so they commute. So we're working with commuting Quaternions because they point in the same way. At least that's my hope. And the reason that we're doing all that work is so we can understand that our wave function is space-like separated from the conjugate of our wave function. All right. Thank you very much.